Hi everyone, this is Mrs. GA, and today we're going to talk about geometric sequences and series. So a geometric sequence is a sequence that can be written in this form. So A in the next term is A times R, then A times R squared, A times R cubed, where A is that first term and R is what we call the common ratio. So this is really just a fancy way of saying to get to the next term, we multiply by the same thing each time, that common ratio. So you'll notice that for each consecutive term, we're simply multiplying by R to get there. So again, that's called the common ratio. So there is a formula that we can use to describe the nth term of a geometric sequence, and it's a sub n equals a sub 1, the first term, times R, the common ratio, to the power of n minus 1. It is really important to note here that the exponent n minus 1 only belongs to the r, not the entire, the rest of the equation, not a sub 1. So it only is r raised to the power of n minus 1. Okay, so let's see if we can use that formula that we just learned to help us find the eighth term of this geometric sequence. So first, we're told that it's a geometric sequence, and we can probably infer that by looking, because each time, at least to get to the next two terms, we are multiplying by 3. So that shows us that our common ratio, r, is 3, and we can see that the first term is 5. So in this case, it's probably faster for us to actually make the formula and use that to find the eighth term rather than to sit here and multiply by 3 until we get to the eighth term. So we can really easily make this formula again. It's just that first term times r to the power of n minus 1. That's our formula. So if we want to find the eighth term, we simply replace n with 8. So we do 5 times 3 to the power of 8 minus 1, which is 7. So make sure you are following order of operations here. We're going to raise 3 to the power of 7 before we multiply it by 5. So the eighth term should be 10,935. Okay, so in example 2, we are told that the third term of a geometric sequence is 63 fourths. So they're telling us that a sub 3 equals 63 over 4. And we're also told that the sixth term, so a sub 6, is 1,701 over 32. And they would like us to find the fifth term. So here we are going to need to make that formula for this sequence. However, you'll notice that we are currently missing the two things we need for our formula. So again, our formula requires the first term and that common ratio. But luckily, we do have these two pieces of information that we can use to substitute and create a system. And again, this is a sub n and the sub number is n. So let's create two systems here. So a sub n, 63 over 4, equals a sub 1, which is unknown, times r to the power of n minus 1. So if n is 3, 3 minus 1 is 2. And then we know a sub n, so we are given another term, equals a sub 1 times r to the power of 6 minus 1, which is 5. So from here, I am going to take the first equation and I'm going to solve for r, or solve for a sub 1. So I'm going to go like this. So we know that a sub 1 is 63 over 4r squared. And then this we can substitute into that second equation. And let's see what we get. So we would get 1,701 over 32 equals 63 over 4r squared, there's our substitution, times r to the fifth. So to solve for r, we can start by multiplying both sides by 4, so 6,804, and then we can divide both sides by 63, and that gives us a denominator of 2016 equals r cubed. Then if you actually take a moment and you simplify this fraction becomes 27 over 8. So we have 27 over 8 equals r cubed. So now we can take the cube root of each side, and we now have our common ratio, 3 over 2. So let's take this and let's sub this back maybe into our first equation here, because we still need to find a sub 1. So we have 63 over 4 equals a sub 1 times 3 over 2 squared. So 63 over 4 equals a sub 1 times 9 over 4. So you can see here that a sub 1 is equal to 7. So now we have the two pieces of information we need to create our formula. So our formula is a sub n equals 7 times 3 over 2 to the power of n minus 1. And this will allow us to find that fifth term. So 7 times 3 over 2 to the power of 5 minus 1, which would be to the power of 4. And that gives us a fifth term of 567 over 16. All right, why don't you take a moment and pause the video and see if you can give this problem a try on your own, and then we will check your answers in just a few seconds. Okay, let's have a look here. So I had to use that same process with this one. These were the two pieces of information we were given, and we still needed to find a sub 1 and r. So I created a system of two equations here. I solved for a sub 1 in the first equation, and I substituted it into the second equation right here. And then here it's just a matter of plugging through to solve for r, which ends up being 5 over 4. And then you can sub that into equation 1 to help you find a sub 1. So a sub 1 should be 3, r should be 5 over 4, and that allows you to create this formula, which you can use to find that fifth term that they were asking for. So this should be your final answer. Okay, so now we're going to talk about how to find a partial sum of a geometric sequence. So the sum of the first n terms of a geometric sequence can be found using this formula. The formula is a sub 1, the first term, times 1 minus r to the power of n over 1 minus r. So again, all you need for this formula, you need to know the first term, your common ratio, and then you should be able to find the sum of the first n terms. Okay, so let's see if we can try using that formula in this example. So here we are given a geometric sequence. So the first thing we're going to want to do is figure out what our common ratio is. And I can see that our common ratio is 0.7 each time we're multiplying by 0.7 to get the next consecutive term. So now we know everything we need to use the formula, again, which is a sub 1 times 1 minus r to the power of n over 1 minus r. So that, again, that's the sum of the first n terms. So we can find the sum of the first 5 terms by doing a sub 1, which is 1, times 1 minus 0.7 to the power of 5 over 1 minus 0.7. So I think for this, the trickiest part is going to be making sure you plug this into the calculator correctly, and you should end up with a sum of 2.7731. Okay, let's see if we can find this sum. It is written a little bit differently. It's written in sigma notation, but here you can see that we are asked to find the sum of the first 5 terms, because remember, this is the term we start with, this is the term we end with. So we are again asked to find the sum of the first 5 terms. So for this problem, we do need to make sure we understand what the first term is. So you can see here, this would be the formula for our sequence. So the formula is 7 times negative 2/3 to the power of, I'll say n in this case because we're calling it a sub n. So to find the first term, we simply replace n with 1. So we can see here that our first term is negative 14/3. We can also see, just based on where it's positioned, that our common ratio, r, is going to be negative 2/3. So this is going to be our common ratio. So now we have the two pieces of information that we need to find our sum. So remember, the formula is a sub 1, so negative 14/3 times 1 minus r, negative 2/3 to the power of n, 5, over 1 minus negative 2/3. And for this one, since we are working with fractions, we can keep it in fractions. So this actually gives us an answer of 770 over 243. So again, just make sure you understand how to interpret this sigma notation, and you should be able to look at this and say, okay, here's my formula. I can use the formula to help me find the first term, and within this formula, this should always be the r value. All right, the last thing we're going to talk about is how to find the sum of an infinite geometric series. So one thing you might notice before we talk about this formula, I've now switched from the word sequence to series. So a sequence is simply a list of numbers like this, and it becomes a series when you start adding them. So this would be a sequence, this would be a series. So it is just a little bit of vocabulary to know, but it involves the same numbers. A series just means you are now finding the sum. So in some cases, it is actually possible to find the sum of a series that goes on forever and ever and ever. However, there is one qualification you have to meet. So in order to find this, the absolute value of r, that common ratio, must be less than 1. So anytime the absolute value of your common ratio is less than 1, for each consecutive term, your terms are going to be getting smaller. You're essentially multiplying by a fraction that's less than 1. So if your terms are getting smaller and smaller and smaller, the idea is way down the line, when you've reached like the millionth term, the amount that you're adding is so incredibly tiny that it's almost insignificant. So we can actually reach a sum. It will approach a limit, okay? So there is the formula for this, and the formula is really, really simple. It's just your first term, a sub 1, divided by 1 minus r. All right, so let's see if we can use that formula that we just learned. So the most important thing when you're doing a problem like this is to make sure it's even possible, and that is all determined by that common ratio. So you can see here that we do have a common ratio of 1/5. And since the absolute value of 1/5 is less than 1, we can find this infinite sum. And you can see, even by the fourth term, 2 over 125 is a pretty small value, and that's only the fourth term. So you can imagine by the time we've reached the 100th or the 1000th term, the numbers we're adding are so small that it really doesn't affect the sum. So that's why we're able to find it. So again, let's refresh what that formula is. It should be a sub 1 over 1 minus r. We see that a sub 1 is 2, and we know that r is 1/5. And then this we can simplify by hand. So 2 over 4/5. So that's going to be 10 over 4, which is 5 over 2. Okay, so now we're going to use that infinite sum formula for a really cool application. We can actually use it to help us write a repeating decimal as a fraction. So you can see here that we do have a repeating decimal that starts after the 3, so the 515151 will repeat infinitely. So first we're going to try to write this decimal as a sum of different fractions. So first we're going to start by writing the part that's not repeating as a fraction. So 2.3, we can write that as 23 over 10. So we've covered up to the 3. So now let's cover the next two terms, or the next two decimal places together. So if I wanted to write those in, 51 over, this 1 goes all the way to the thousandths place. So this would be 51 over 1,000. And then we need to add the next chunk of our repeating decimal. So this would give us 51 over 100,000. And then let's add on one more. So this last one here would give us 51 over, that goes to the 10 millionth place. So you can see that this pattern would just keep continuing. So when we write it like this, although this first part, the 23 over 10, doesn't quite fit in, from here, from red on over, we can see that this is actually a geometric sequence because there is a common ratio. So let's see if we can describe this sum. We can find the sum of the part that is geometric. So for this part, we can see that the first term is 51 over 1,000. And then we can see that the common ratio is 1 over 100. So each time we're just adding 2 zeros to our denominator, and that's because we're moving 2 more places over in our decimal. So since we know the first term and we know the common ratio, we can find the infinite sum of from here on to the right. And again, we do need to check that our R value works, and it does. So we can find that sum by doing 51 over 1,000 over 1 minus 1 over 100. So that becomes 51 over 1,000 over 99 over 100. And then if you multiply by the reciprocal of the denominator, that should give you 51 over 990. So this gives us the sum of everything from here to the right, but we still need to make sure that we add it to that original part in the front. So we have 23 over 10 plus 51 over 990. And if you add those and make sure it's simplified completely, you would get the fraction 388 over 165. And then of course you could double check this by plugging this into your calculator, and you should get this repeating decimal. But again, the idea is to write your repeating decimal as a sum of fractions, and then hopefully you can notice a pattern that is geometric, allowing you to use the formula we learned. Okay, so here is the last you try. Go ahead and pause the video and see if you can find the sum of this infinite geometric series. All right. So of course the first thing to check is that it's even possible. The R value is 1 over 9, so this is possible. And so we simply use our formula, a sub 1 is 5, R is 1 over 9, and we should get a sum of 45 over 8. Okay, that is all for today's video. Thank you so much for watching.